This is section 5.1.1, divisibility and prime factorization. Here's some vocabulary basics that we need to cover before we get into divisibility and prime factorization. The set of counting numbers are called natural numbers. You can see here capital N represents the natural numbers, and they are the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on, going all the way to infinity. The natural numbers that are multiplied to get the product are called the factors. A couple examples: 2 times 12 equals 24. That means 2 and 12 are factors of 24. 3 times 8 is also 24. Therefore, 3 and 8 are factors of 24. And finally, 6 times 4 is 24. That means 6 and 4 are also factors of 24. Now we're ready to define divisible. If A and B are natural numbers, A is divisible by B if the operation of dividing A by B leaves a remainder of 0. This definition is a little bit wordy, so make sure you read it carefully and understand it. If you need to pause the video now and read it over again, do so. The definition above is the same as saying that B is a divisor of A, or B divides A. All three statements above can be symbolized this way. Make note that this is not a division symbol. It is simply a line stating that A is divisible by B. Here's an example. 24 is divisible by 8. We can also say 8 is a divisor of 24, or 8 divides 24. And as you can see, we write all three of these statements the same way. Of course, these are true statements because 24 divided by 8 is 3 with no remainder. Here are some rules of divisibility. These rules can also be found in your book on page 194. Some of these rules you probably know already. For example, divisible by 2. Of course, the test for this is that if the last digit of the number is a 0, 2, 4, 6, or 8. In other words, an even number. Divisible by 5 is probably another rule that you already know. If the number ends in a 0 or a 5, then it's divisible by 5. Divisible by 10 is probably another rule that you know. Of course, if the last digit of a number is 0, then we know it's divisible by 10. These other rules of divisibility can be handy when working with numbers. If needed, refer to your book on page 194. Let's put our rules of divisibility to work. We're going to determine if each of these numbers is divisible by 5, 2, and 9. Let's start with number 1, 6,944. Is that divisible by 5? No, of course it's not. If you remember, the rule of divisibility for 5 was that the number had to end in a 0 or a 5. Of course, this number, 6,944, does not. How about divisible by 2? Yes, it is. Of course, 6,944 ends in a 4, which is an even number. Therefore, this number is divisible by 2. Finally, let's see if it's divisible by 9. Let's go back and look at the rule of divisibility for 9. The sum of the digits is divisible by 9. So, what this means is we're going to take the sum of the digits of this number. Six plus 9 is 15, plus 4 is 19, plus another 4 is 23. Is 23 divisible by 9? No, it's not. Therefore, 6,944 is not divisible by 9. Let's go to our second example, 7,245. Is it divisible by 5? Of course it is, because it ends in a 5. How about divisible by 2? No, it's not, because it ends in a 5, which is an odd number. Therefore, it's not divisible by 2. How about divisible by 9? Well, we know that we need to add up the digits of the number. 7 plus 2 plus 4 plus 5. 7 and 2 is 9. 9 plus 4 is 13. 13 plus 5 is 18. Is 18 divisible by 9? Yes, it is, because 18 divided by 9 is 2 with no remainder. Since the sum of the digits is divisible by 9, we know that 7,245 is divisible by 9. And finally, our third example, 89,001. Is it divisible by 5? No, it's not. How about by 2? No again. Is it divisible by 9? Well, let's add up the digits. 8 plus 9 plus 1 gives us 18 again. Of course, we know that 18 is divisible by 9. Therefore, 89,001 is also divisible by 9. Prime and composite numbers. A prime number is a natural number greater than 1 that has only itself and 1 as factors. The first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Each of these numbers is only divisible by itself and 1. A composite number is a natural number greater than 1 that is divisible by a number other than itself and 1. The first 10 composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18. Prime factorization. Expressing a composite number as the product of prime numbers is known as prime factorization. One method to find the prime factorization of a composite number is to create a factor tree. Let's take a look at doing this. Here we have 3 examples. We're going to create a factor tree to find out the prime factorization of each of these numbers. Let's start with 120. Now, when creating a factor tree, the goal is to be able to factor the numbers down into only the prime numbers. So, one method of doing this is to factor the number into into 2 numbers, one of which is a prime number. So in this case, we want to factor 120 into 2 numbers, one of which is prime. Well, a very simple way to factor it is 2 times 60. We know that 2 is a prime number because it only has itself and 1 as factors. 60 is a composite number, so we need to factor it again. Once again, the prime number 2 is a factor of 60, 2 times 30. 2 is prime, 30 is composite. Now we can factor 30. Well, you may want to do 2 times 15. Again, 2 is prime. And now 15. 3 times 5. And in this case, both 3 and 5 are prime numbers. So what we know is that if we take 2 times 2 times 2 times 3 times 5, we'll end up with 120. So we have factored 120 into 5 prime numbers. This is the prime factorization. 2 times 2 times 2 can be written as 2 to the third power times 3 times 5. And this is the answer, the prime factorization of 120. Now let's take a look at the number 56. Once again, we want to create a factor tree. So we're going to factor 56 into 2 numbers, one of which is prime. 7 times 8 is 56. 7 is a prime number. 8 is a composite number, so we need to factor it again. Think about the prime numbers. 2 times 4 is 8, and 2 is a prime number. 4 is a composite number, so we need to factor it again. And in this case, 2 times 2 is 4, and both of these are prime numbers. So we know that 7 times 2 times 2 times 2 equals 56. We can rewrite this prime factorization as 7 times 2 to the third power. And finally, our last example, 3,675. Now this is much bigger than the previous 2 numbers. However, you shouldn't worry, because if you know some of your prime numbers, and you know some rules of divisibility, you can clearly see that this number ends in a 5, and so it's divisible by 5, and 5 is a prime number. So we can factor 3,675 into 5 times 735. Now, of course, if you need to use a calculator to do 3,675 divided by 5, go ahead and do so. 5 is a prime number. Now, 735 is a composite number. It ends in a 5, so once again, we know it's going to be divisible by 5. So we can factor it into 5 times 147. 5 is prime. Now, 147 is a little bit of a tricky number. It no longer ends in 5, so we have to find 2 factors, one of which is prime. You need to take a minute, review your prime numbers, as well as some rules of divisibility, and see what factors we're going to use. It also might help to grab a calculator and start doing some division. 147 divided by 2, 147 divided by 3, and so on. By doing this, you will find that 147 factors into 3 times 49. 3 is a prime number. 49 is a composite number. And it just so happens that 7 times 7 is 49, and both of these are prime numbers. So we can write the prime factorization as 5 squared times 3 times 7 squared. And that'll give us 3,675. This is our prime factorization. As you can see from these 3 examples, you need to know your prime numbers very well. You need to understand some rules of divisibility, and you need to be able to do some division with a calculator. Finally, the fundamental theorem of arithmetic. Every composite number can be expressed as a product of prime numbers in one and only one way. The order of the factors doesn't matter. What this means is that the three examples on our previous page could have different factor trees, but in the end will have the same prime factorizations. In other words, the fundamental theorem of arithmetic says there could be different work, but there's only one answer. This has been section 5.1.1, Divisibility and Prime Factorization.